All right, so welcome back to the OneClass stream. Again, this is pre-calculus and trigonometry for the US curriculum. My name is Joey. I'm going to be your math teacher for today and for today's session. Just a little bit about me before we start. Again, I'm currently a teacher candidate at York University, specializing in the intermediate senior division, in particular subjects such as chemistry, so in science, and music as well. However, I am planning to get my math teachable further down the road. And just a little bit about OneClass if you're just tuning in for the first time. Again, OneClass is an online platform where students of any learner of any kind, so learners of any age, can access our videos, particularly in chemistry and in mathematics and other preparatory courses as well. These videos are all free online, and we stream from Monday to Sunday, so you can tune in whatever at your time. Right now, currently it's 10 Eastern, and whatever that time zone might be for you, if you're tuning in from around the world. And you can participate in this lesson and watch in this chat and type in this chat any questions you have about these subjects, and I'll try my best to answer your questions. And yeah, that's kind of a little bit about OneClass. And without further ado, let's just get started and continue off where we left last time. So what we left last time was we did some transformations of graphs. So what we talked about, just a little review about last lesson, was we talked about how we can the definition of changing the size and location of a function. So in this case, we're talking about transformations of a function, and I took the example of x squared because that's what a lot of you students might be familiar with a quadratic function, because we've talked about this function in the past. So I was hoping that we could use this function again and to help learn this concept of to help teach this concept, of the transformation. So what we have here is we talked about first our vertical and horizontal shift. So again, just to review, vertical shifts is if I have something like x squared plus a constant. If it's a positive number, I'm going to shift up vertically by a factor of the constant. So 1, 2, and what d is. So if d is 1 in this case, in this example, I'm shifting up by a factor of 1. Or actually by 1 in this case, sorry, not factors, just by 1. And then if it's a negative number, if d here is negative, for example, negative 3, I would shift down by 3. So that's a vertical shift. And we looked at, we used Desmos, right? What we did was, I have here x plus 1 squared, but what I can do is if I filled in x plus 1 squared plus 1, you realize that the shift here is moving up by 1, and if I change this to minus, it's going to move down by 1. So, and we use Desmos here to help this graphing calculator to help us visualize very, very accurately transformations of functions. So again, this is the vertical shift. So we have vertical shift as our first shift here, and then we talked about horizontal shift, right? So if again, if I have x plus 1 squared, and if I want to shift what this does to my graph here is it shifts left by 1, right? So if my parent function is in the blue, if I have a plus 1 here, it's actually not going to shift right, but it's going to shift left, right? It's going to shift left by 1 here, because here we have x minus c, right? So negative c means it's left, right? And I proved that algebraically for you. So if I said here if c is greater than 0, then I would get f of x is bx minus c. So this what it would do is it would, if c is greater, oh, I think I confused this. Sorry, I'm just looking at this. Oh yeah. No, I'm good. If c is negative here, or if c is positive here, it's going to shift left. If c is negative, it's going to shift right. And it's so that's, again, this is just inspection, right? So if we're looking at x plus 1 squared, we have here, this is positive 1. This is a positive number in this bracket, and what we're doing in our header is we're going to flip it. So we're going to flip it to negative, and when we do that process, so a positive number means it's moving left at a positive number is moving right at this point. The transformation is moving left. Sorry, I got confused now. So you see here it's moving left, and then the negative number in this bracket is going to move right by 1. That's horizontal. Sorry, that's horizontal shift. And then we talked about reflection. Sorry, we talked about reflection on the x and y axis, right? So we talked about reflection on x axis. So again, we have the entire function is reflecting on the x-axis. So it's going from this way, and then it's going to moving down, right? So I visualize that with your. I have let's put a negative here, so it reflects. Sorry, reflects on the x-axis, as you see here. So it's being reflected, right? It's moving from this side of the plane to this side of the plane. So it's reflected on the x-axis. And then we talked about reflection along the y-axis as well. Along the, did we talk about reflection on the y? Oh yeah, we did. Reflection along the y-axis is a negative, negative in front of it, right? So it'd be negative like this way as well. So that's what we did in our reflection along the y-axis. So that's cool. So that's neat. So now what we're going to do is I'm going to introduce one more concept. I'm going to introduce the concept of this is this is going to be horizontal and vertical compression. So let's talk about stretch and compressions first. So let me just write here. This is a point. So I'm going to do it in blue. This is 3. And we're doing stretches or expansion. Some of you might be known as. So stretches. I'm gonna write here expansions, and then it's compressions. And then there's 2 types. There's a vertical one and there's a horizontal one. So it goes in both planes. So let me break this down. So we have one that's vertical. And then we have one that's horizontal. So how do we do this? How do we have to break this down, right? So let's do the vertical one first. So let me do a sub point and say that let's focus on vertical. Or actually, let me erase this and let's do vertical first. Actually, I'll do this in red. This is a vertical stretch or compression. And then I'm going to use the function here. It's going to be, again, f of x. I'm going to model it with f of x equals x plus 1 squared. X plus 1 squared. So we have this function here, f of x equals x plus 1 squared, and we're talking about vertical stretches and vertical compression. So what does that mean when we talk about vertically stretching or compressing? If you think about a parabola, again, if you think about a parabola, I'm going to delete this. That's like this. If I'm stretching it vertically, what does that mean? So again, I'm on the y-axis because that's what it's talking about along the y-axis. And what does it mean to stretch it? If I'm stretching the parabola, you can say that I'm making it thinner, or it's becoming thinner, right? So how would I do that with this function? So it turns out algebraically, what that means is whenever I vertically stretch something. So if I have f of x equals x plus 1 squared, if I vertically stretch, so I'm going to do a subpoint and say stretch. If I stretch this function here, this would become, I would stretch it by a factor of something. So let's say a factor of 2. So factor of 2 and then x plus 1 squared. So this 2 here, before the entire function stretches it vertically, and I'll show you what that means here. So I'll have 2x plus 1 and then squared, and as you can see, my parabola here became thinner, right? I'm stretching it vertically, and this was what it means by when I want to talk about stretching it vertically. If I stretch vertically, it's becoming thinner. So my parabola here is becoming thinner because I'm stretching it vertically. And then if I want to expand it, so in expansion, compression. I'm getting confused now. This would be so that's stretch, and then what if I compress? Compress would be f of x, and it would be a fraction in front of this instead of the 2. So in this 2 here, if this value here is greater than 0, it would be, greater than 1 in this case, and this would be a stretch. And if the value is between 0 and 1, it's going to be a compression. So let's put a half here, half x plus 1 squared. And if I put it into my graphing calculator, you're going to realize that this function is going to become thicker. So again, thin would be vertical stretch. Vertical compression is it makes the parabola thicker, so it opens up more, you can say, whereas stretch opens up less. So you can think of it as like a weight kind of thing, pushing on the parabola. If I push and compress the parabola, it's become thicker. If I loosen my weight above it, it's going to become thinner. And that's how I kind of think about it. So this point here, so you can say that vertical stretch is a thinner graph. Thinner. And this one is thicker. Or maybe I'll do 2C's for you, for those of you who get that reference. So again, thinner would be, again, vertically. Again, this only applies to the vertical plane. So when we're talking about playing with the values in the y-axis, again, it's thinner, or as we stretch the graph, and as we compress the graph, it's going to become thicker. So I'm going to create now rules for you for vertical stretch and vertical compression. So every time we see a stretch here, so the value, I'm going to say this, I'm going to set this as like, I'm going to set this as a, this value is a, so if a is greater than 1, if a, I'm going to put absolute value bar, so a is greater than 1, you're going to get a vertical stretch. Vertical stretch. And then if a, sorry, give me a second. Bless you, bless me, sorry. If a is less than 1, it's going to compress. But I'm sorry, if a is between 0 and 1, it's going to compress. So if it's between 0 and 1, it's going to be a vertical compression. And then what if it was negative? What if it was less than 0? Sorry, if it was less than 0, I would get it would flip upside down, right? I would get a reflection, right? We talked about this topic of reflection, right? So if it would actually reflect on the x-axis in this case, it would reflect on x-axis. So with this graph, when I include this one, when I include vertical stretch compressions, if it was a negative and a constant number, so if it was negative, like -3, and then I have x plus 1 squared. So let's take, for example, here, this is the parent function again, x plus 1 squared. If I took -3 and I put x plus 1 squared, as you can see here, my function did 2 transformations. So you can do this in any order you want, but I see this negative here. So it's going to flip along the x-axis. So it flips from this plane to this plane. And as we can see here in green, it flips it upside down. And then it's going to, and then I'm going to not move the function, but I'm going to vertically stretch the vertically stretch the function, so it becomes thinner, right? So as you can see here, remember, stretch here is thinner, right? If I have a vertical stretch, because again, I still have that 3 here, right? It becomes thinner. So it did 2 transformations. I flipped it upside down and I stretched it by a factor of 3. So again, this would be an example of vertical stretch and compression. So again, we have vertical stretch compression. Obviously, we're gonna have horizontal stretch and compression. So let me write that down. So this is horizontal. Sorry. So this is a horizontal stretch, or I use stretch here, but it's actually expand as well. We use those terms interchangeably in this course. So horizontal stretch and compression, and what that is it. So it's going to, I'm going to stretch and compress not in the y-axis, but in the x-axis. And what it does is it actually flips these rules. So it's kind of mean to us algebraically, but it makes sense as to why it's doing that. So I have here again, I have f of x equals x plus 1 squared. So if I wanted to do a horizontal stretch, so let's do this is a horizontal stretch. This number, instead of being in front of the function, it's going to be in the function. So I'm going to write here a bracket, and then I'm going to put here half x plus 1 squared. And if you look at that, and if I plug that into Desmos, I'm going to get half x plus 1 and then squared. If you look at this function here, what it did was I have here a horizontal compression. Sorry, a horizontal stretch. So I'm stretching it like this way. I'm stretching it this way, and then compressing would be I'm flattening it. So again, a horizontal, and then this is horizontal stretch, and then compression would be this way. So as you can see, this is a horizontal stretch. Again, my function is now becoming thicker, right? So I can say here, this is the opposite. So remember how vertical stretch was thinner, horizontal stretch is thicker. So I'm gonna write here, thicker. And then as you can probably tell from the pattern here, a compression would be thinner in the horizontal plane. So a horizontal compression would be thinner, and then that would be if I had a value of, if this was greater than 1. So I'm going to write 2x plus 1 squared here. And then this here I'm going to write, and we'll prove that for you. This is a thinner. So as you can see, and you might be asking me, wait, Joey, if I'm horizontally stretching something and I put half x plus 1, why is it being moved? Why is my vertex being moved? So as you can see here, this is 1, 0, and this here is 2, 0. Like, why is there I'm moving it? Isn't this just a moving in the x direction, a horizontal shift? And we might be saying, yes, it is a horizontal shift, but however, this is a horizontal stretch as well. And I'll prove to you what that means algebraically. So if I had this function here, and I'm going to do a little side note, maybe so this can be in blue. I'm going to shift everything this way. I'm gonna copy what I have here. So I have here half x plus 1 squared. And I told you that if it was a fraction between 0 and 1, it's going to be a horizontal stretch. However, what I can do to this function is I can actually factor out this half, right? So if I factored out this half to the outside, I would get half, and then I have x plus, and then what do I have to multiply to get 1 here? I have to multiply 2, right? 2 times half is 1, right? So I have to put 2 squared. And as you can see, this looks like a lot like a different function, but in reality, it's actually the same function. So remember, these two are algebraically equal to each other. So these two are algebraically equal. One says I have a horizontal stretch. So this is a horizontal stretch. However, this function, look, if I have half here, what is this? This half here before the function states that I have a vertical compression, right? I have a vertical compression here. Vertical compression. And then this plus 2 is different from the plus 1. Instead of moving left by 1, I'm going to move left by 2, right? But in this case of difference, it's going to move by more left by 1, right? So I'm going to say more left by 1. And as you can see here, by more left by 1, I'm shifting 1 more to the left, and then I'm also doing a vertical compression, right? As you can see, vertical compression makes it thicker, right? Vertical compression vertical compression makes it thicker, right? And as you can, that's what I got here, a vertical compression. So what I could do is I could write a horizontal stretch in this case is exactly the same as if I did 2 transformations to this function. If I did instead of 1 horizontal stretch, I did a vertical compression and I did a horizontal shift, right? So again, a lot of these stretches and compressions can be modeled algebraically into a different transformation. So as you can see, again, this algebraically, this equals this is the same function, right? However, how I choose to visualize it is different. I could choose to say I horizontally stretch this function and I made it thicker, or I could say I vertically compressed this and I shifted it left by another by 1 again, right? So again, this is this is another way to model these transformations. And this kind of gets kind of confusing, but what we have to do is we can solve for it algebraically before we state the transformation. That's what we're doing in this case. So that's it for all my transformations. So let's do a little review of what I have, and then we'll jump into these questions here. So again, we have 3 types of transformations. We have vertical, horizontal shift. I'm not going to go over this because we did that already. We have a reflection of x and y axis. And then the third one is stretching and compression in the vertical and the horizontal. So again, with the vertical, if I had a constant that's greater than 1, it's going to look thinner, but my number is before the function. If it was a fraction, so between the numbers 0 and 1, it's going to be a thicker function. It's going to be a vertical compression. And then this number would be this value here would be a fraction. Again, all these numbers, all these a values are always, this is a vertical stretch compression. It's always, no, the a is before the function. So again, it's a here. And then for horizontal stretch, it's going to be you can think of it as like the letter B, and it's going to be inside the bracket, right? And again, if I do the horizontal stretch, it's going to make it thicker, right? It's going to make it thicker. And if I did a horizontal compression, it's going to make it thinner, right? So horizontal stretch, again, it's a fraction in the brackets. So in the function, it's going to be a horizontal stretch, makes it thicker. And then if it's greater than 1, it's going to be a horizontal compression, and that value is inside the bracket. And we're going to do a lot of practice with these rules, and we're going to refer to a lot of these rules before we kind of start memorizing, just get them in your head. So let's do number 1 here. Number 1, and I'm going to have to zoom in a lot. I'm only going to do number 1 because 2 is kind of cut off, and I guess we can do 1 and 2, but let's do number 1 here. So it says here, describe the transformations necessary to transform the graph of x to whatever g of x is, which is the dashed line. So how do I go from here to here, right? So let's do that. So number 1, again, I have here, I believe this is x squared. Yes, this is the function x squared, because I see 2, 4 here, and I see 1, 1. So my function here is, I have x squared as my first function. So f of x equals, I believe it's x squared. And we don't have to actually show them algebraically. What it tells us to do is just describe the transformations necessary. So I'm actually not going to do this algebraically. We'll do that in the other problems. But I'm going to describe the function. So what's happening here? So to maybe take a minute, if you're in the chat, let me know if you're in the chat, if you're here. Let's talk about, I see here 2 transformations that are needed to get this dotted line. So maybe if you're in the chat, maybe think about it for a minute, and then reply with your answer as to what you think the transformations are necessary to go from this blue line to this green dashed line. So how I visualize it, I see 2, and you can visualize it differently, but in all cases, how I choose to visualize this, the first thing I see here is I see a reflection. I see a reflection along the x-axis. I see a parabola going this way, and then it's going to flip downward. So I see a reflection along which axis? It's not left to right, but it's up and down. So this is a reflection along the x-axis. So I'm going to say here. So the first one, I would say here, the first step, so number 1, maybe a bullet point, is reflection on, and I'm going to say x-axis. So that's the first transformation I need to do, reflection along the x-axis. And what's my, I said I need 2, right? What's my second transformation? What do I need to do? So as you can see, the vertex of my parabola is 0, 0. And in this case, the vertex of this parabola is -3 and 0, right? So again, this vertex is shifted left horizontally by 3, right? So I can say here, a horizontal shift, or in this case, it's to the left by 3, right? So horizontal shifts. Some of you may use this word translation. So translation is the same thing as shift. So it's okay. So I can say here translation shift, and then I'll write little a. Translation works as well. So translate left by 3, or shift left, horizontal shift left by 3. So this works. So that's what we have in the first one. And what about the second one here? Let's do the second one as well. So second one, what I can do is, in this case, I had a parabola, right? So this is a quadratic, and what we're doing is we're quadratic function. And what about this function here? That's not -2, sorry. What's 2 here? What is this function called first? Let's look at this function. Let's not talk about the transformations, but this function looks like it's an absolute value function, right? So an absolute value function. So remember, something like f of x equals absolute value of x, right? And I think that's what we have as the blue line in this case, which is nice. So what transformations do I need to get the green one? What do I need to do? So the first thing I see is I see it being it's a thicker function, right? So a thicker function, and what I see here is I also see a shift in vertex. Right? In this case, the vertex here was 0, 0. It's now going to 0, 3. So maybe I'll do the shift first. So I'll do the shift first. So it's going to be vertically shifted. That's a really bad A. So this is a vertical shift, and I can say it's up by, this is by 3, right? So it's going, because it's 0, 3, or I can just say translate up. It doesn't matter. Vertical shift by up, translate up by 3, doesn't really matter. And what is the other thing I see here? I can see the function being thicker, right? And it doesn't. And again, would this be a horizontal one or a vertical one? In this case, I would say it's going to be a vertical. I'm going to say here. Let's see. Let's go back. Let's go back to my graph here. So this is so it could be a vertical stretch, or sorry, in this case, it's a lot thicker, right? So it opens up more. So I can say it could be a compression, a vertical compression, which I think it is, or it could be a horizontal stretch. In this case, I don't think it's a horizontal stretch, because remember, if we had a horizontal stretch here in this case, it basically becomes a vertical compression, and it moves left by 1. I'm not moving anything. It's not being moved. The vertex is not being moved horizontally, it's only vertically. So in this case, I would say it would be a vertical compression by a factor of, in this case, it's by a factor, I want to say it's actually 2, right? Because if you look at, I have a point that's 0, 3. My next points that intersect is 6 and 6 here. But as you can see, it travels much faster by a factor of 2, much faster than this function here. So if I looked at this point here, this point here, this is 2, 4, while this is 2, 2, right? So again, I have a vertical stretch, right? I'm changing my y values. This was 2, 2. So here, let me write this down, because this is really important. So how do I find out what the number is? Like, I don't know if it's 2, 3, half, whatever. So my original function, I had the point. So what I do is I take 2 points. So I'm going to take here, this point is 2, 2 in this case. So my original function, OG function, was 2, 2, and then transform function. So TG here, in this case, this 2 here becomes 2, 4, right? Again, I'm not changing my horizontal values, I'm changing my vertical values. And as you can see, 2 times what equals 4? It's going to be a factor of 2, right? Which means I'm doing a vertical compression, so not a horizontal stretch, by factor, and this is important, I have to write factor of 2, and that's what I'm doing here, vertical compression by a factor of 2. And that's how I'm kind of solving this. So that's 1 and 2. Again, we had an absolute value function for number 2. We're vertically shifting it up by 3, and then we are compressing it, so making it thicker by a factor of 2. So let's do these questions here. And it says here, describe the transformations necessary to transform the graph from f of x into g of x. And we're given this algebraically. So how do I do this algebraically? What if I'm not given a graph? So let's do number 3. So this is f of x equals root x. So again, this is a square root function, and we're very familiar with that from our power functions from last lesson. And then we have here, I'm going to use some blue. This is a g of x equals this -3 square root x, and then -1 is outside the bracket. So I'm going to do a little hook here saying that this is -1. So what transformations do I need to do to go from f of x to g of x? So again, take a minute to figure that out. I'm going to put my notes back up here. So if you want to refer to them as well, you can. And I'm going to put specifically this one here. So how would I get to from f of x to g of x? And I can actually show you on Desmos how we do that and to verify our answer graphically, but we have to be able to see it algebraically as well. I see 3 transformations in this case. So I usually work from left to right. So let's do that. So from left, I see here, I see this negative here, right? And this is in front of the function. So what does that mean? Let's scroll back up to our reflection. It's going to be a reflection, but it's on the x-axis or the y-axis. In this case, if it's ahead of before the function here, it is reflection on the x-axis. So let me write that down. That's my first thing I do. I reflect it. So in order to get g of x, what I'm going to have to do is number 1. So my first point, I'm moving from left to right. Again, you can do these transformations in any order you want. I just choose to do from left to right here. So I'm reflection along the x-axis. So that's my first one here. So that take care of the negative. What about the 3 here? Again, this number is greater than 1. So this is 3 here. This would be if it's before the function, this is a vertical stretch. So vertical expansion, stretch, it doesn't really matter. So a vertical stretch, and this is by a factor, and this is of 3, right? By a factor of 3. Every time we talk about stretchings and compressions, it's not just simply, by 3, it's by a factor of 3, because I'm multiplying all these numbers, as you can see, all these numbers by 2, right? So this was 2, 2, this becomes 2, 4, 3, 3 becomes 3, 6, 4, 4 becomes 4, 8, etc., etc. So that's what we're doing in this case here. So vertical stretch by a factor of 3, and then what's left here is I have what's this -1 here doing? Because I have root x here, right? This doesn't change here. What's this -1 here doing? This -1 would be this is a vertical shift, right? And in this case, it's downwards, right? Because this is a negative number, it's going down. So the vertical shift down, and this is simply by 1. So I have, or you can say translate down by 1. So as you can see, I have three things here. So the reflection along x-axis is denoted by the negative sign in this case. So this negative here. By vertical stretch by a factor of 3 is denoted by this 3 here. And vertical shift down by 1 is denoted by this -1 here. So you can see how my the three transformations are reflected algebraically in g of x. I'll give you a moment to digest that while I write down number 4. So this is f of x equals is x cubed, and then I have I'll do g of x in blue because this is a different function. This is g of x equals 3x plus 1 cubed. Sweet. So let's move on to this one. How would I transform this function? So this is x cubed. Actually, no, sorry. I was going to show this on Desmos, right? So let me do that real quick. So I'll show you that I've verified this function, and I'll verify that graphically for you. So square root x is this function here. square root of x, and then doing -3, so -3 square root of x, and then it's just, this is -1, right? So that's, so the purple one is what we did to this function. So as you can see, I did 3 things, right? And we can verify. Reflect along x-axis, correct. I'm going from this side to this side, so I'm reflecting up and down. As you can see, this one's going downwards, so that's good. I'm vertically stretching by a factor of 3. As you can see, this here, maybe I'll do it. I'm going to do 3 square root x to show you what I mean by vertical stretch. As you can see, this is being vertically stretched, right? I am lessening my weight vertically, and as you can see, it's being stretched this way, right? And so that's what it's doing, but it's doing it in the opposite direction. And then I'm moving down by 1, right? So I moved it, this is down by 1. So as you can see here, the vertex, or whatever it's not the vertex in this case, but where the function started, it's from 0, 0. This is now 0 and 1, right? So again, these 2 points, 0 and then 0, 1, it's being shifted down by 1. So this here reflects this. I am definitely correct. Again, on a test, you won't be given a graphing calculator, obviously. So we need to know this algebraically to show you. So as you can see, I can check my answer graphically as well. Okay, so let's do this function here. So I have x cubed and the 3x plus 1 cubed. So what are I see 2 transformations I need to do. So what do I need to do to get it to 3x plus 1 cubed? So if you're in the chat, let me know what you find or what your findings are, and then we'll share and discuss in about a minute or so. So let me just write down 2 things to happen. So what 2 things do I need to happen to get to g of x? Let's see. So I'm working from left to right again. I see a 3 here, right? And I see this 3 here. It's before the function. So I have it's vertical stretch or compression, but it's a stretch or compression. In this case, it's a stretch, right? My number is greater than 1, sorry. So I have a vertical stretch or expansion. Doesn't matter what you say. So I'll do vertical. Actually, I'm going to write expansion because I haven't wrote that word because I kept using stretch. I'm going to do I'll say a vertical expansion for you to use this term, expansion. And I'm going to say by a factor of 3. By factor of 3. So that's that denotes this 3 here, right? And then what about this plus 1? What does this plus 1 do? And it's in the function. This plus 1 is in the x because everything is being cubed, right? So would this be a vertical or horizontal shift? Again, if it's in the function, it's going to be a horizontal shift because vertical would be outside the function, right? So this is a horizontal. Or I'm going to write translation here just because we haven't used that word yet, and some of you might use that word. So translation, so translate, and what direction? Is it left or right? Right, because we know it's horizontal. If I see a positive number in my function, I'm going to, in my head, I think positive is right? But I'm going to flip that. I'm going to just say that it's going to go left, and that's what it is, right? It's going to translate left by factor of, not a factor, by what number? By 1, right? So it's going to translate left by 1. And what this is this helps me visualize this positive 1 here. So let me graph this for you again. So my function here is I have x cubed, and then my transformed function is 3 here, x plus 1 cubed, right? As you can see here, the red one's my transformed function, but as you can see here, I have x cubed. My little thing here is 0, 0, and then now it's shifted left by 1, so now it's -1 and 0. It changes my x number here, and it's a little bit hard to see, but there is a vertical expansion by a factor of 3. And let me give you a point to show why that is, and I'll give you this point 3. So this here 3. This is 0 and 3. And then I had, where does 3 happen again? 3 happens way up here. No, that's 2. way up. This here is 3. Let's see, hold up. It's going to expand in the vertical direction, and that's why it's hard to see in this graph, just because if I multiply my y value by a factor of 3, it's going to go way up. So I think maybe if I zoom out, it might give you a better idea. I'm trying to think of which points to show you. This is 0, 0. That's not good. That's 0, 3. I need something that changes. 0, 3, and where does the function become 3 here? It's a bit hard to see, but it is being. Maybe if I zoom really out. No, it doesn't really. You don't really see it. Or maybe if I zoom in, it might help. Yeah, if I zoom in, it might help, right? So again, as you can see here, it becomes a little bit thinner, right? Like look at this curve here, and look at this curve here. This curve here is definitely the entire function. This is a thinner function, right? And as you can see here, a vertical stretch here is thinner than my parent function. So that's how it's a bit harder to see in this case. But remember, if I go back to vertical, this was a vertical stretch, it becomes thinner, right? So again, that's I proved that using this is a thinner than the parent function. So again, this was a bit harder to see, but it's there for sure. Okay, so number 5 and 5, 6, 7, 8. Let's just do these two for the sake of time. So 5 and 7. Let's do 5. So I have here, this is f of x equals x squared, and it's going to tell me I have to expand vertically by a factor of 3 and then translate down by 3. So how would I do that? How would I write g of x? So what I'm doing now is I'm given my transformations. How would I do it algebraically? So what would g of x equal? So I always have x squared here, or would I have x squared here? I would have in this case x squared. How would I show expansion vertically? And I'll show my transformations in red. Expansion vertically means vertical expansion, vertical stretch by a factor of 3, which means my 3 would have to go outside the function. So it would be 3x squared. So again, this note denotes my vertical expansion, just like this question here. And how would I translate down by 3? If I'm translating down, this is a vertical shift up or down, and it says down here by 3. So vertical shift, again, I know algebraically it's going to exist outside my function. So I'm going to just put simply minus 3, right? It's going down by 3. So it's 3x squared minus 3 is my answer for number 5. Actually, these ones are quick, so maybe I'll do all of these ones actually just to give you a little bit more practice. So number 6 here would be, this is f of x equals 1 over x. How would I get g of x? So it says here, it says compress horizontally by a factor of 2. So compress horizontally by a factor of 2. What does that mean? If I'm stretching compression is always a number, right? However, in this case, it's horizontal. So if it was vertical, it would exist outside the function. A vertical stretch, for example, would have been 2 over x, right? This 2 is outside my function. I could factor this 2 out, and I would still get this. That's how I get this function here. It's the same thing, right? So again, this would be a vertical stretch. However, I want a horizontal compression. So if I want to do a horizontal, it has to be in the function, right? Which means this here, 1 has to be, this here has to be a 2, right? This 2 here exists like that. And then how would I do translate by 3? So if I'm translating by 3, I'm moving horizontally by 3. And again, it's a horizontal moving left, which means my algebra in this case, if I'm translating left by 3, I'm thinking negative because it's in the negative. Left is negative, but I have to flip it in my head. So algebraically it says positive. So this here says x plus 3. And this actually, it's in the entire function being translated by 3. So I have to put brackets around that. So this is 1 over 2 times x plus 3. And I can show you again on Desmos what that means, right? 1 over x, and then 1 over, this is 2x plus 3, right? Ooh, that's my stomach. And as you can see here, my absolute function is being shifted, right? This is the green one is my parent function, right? 1 over x. And as you can see here, it's moving. It moved, this point you've moved here to, this is negative 2 and 5. I want to find, where's my 1, 1? 1, 1 is here. And now my 1, 1 would be, this is 1, yeah, this here is 1, 1. That's 1, 1, and it's moving. It moved left by 3, so this would be here. This is now negative 3, negative 3, or negative 2.5 and 1. And the 2.5 means that it's being horizontally compressed by a factor of 2, and that's why it changes here. So those are the two ones. This one, again, a little bit hard to see, but it does exist algebraically. So let's do number 7 and the 8. Then we'll move on. So this is 7. F of x equals as the absolute function of x. Oh, sorry, my absolute function of x. And then I want to get what is g of x? What is my transform function say algebraically? There's 3 of them here. So let's go from again. I go from up to down. So it says here expand horizontally by a factor of 2. When I think of horizontal expansion, I have to think of it as it's being stretched, right? Horizontal stretch by a factor of 2 means that it actually here algebraically it means half. And why do we mean by why am I changing this number? If I go back to my rules here, it says here horizontal expansion. A horizontal stretch means that I have a fraction in it's 1 over b, right? In this case, 1 over whatever value this is. So the horizontal stretch makes it thicker, and it needs a fraction. It has to be between 0 and 1, right? So this, if it's a factor of 2, I would have to make it 1 over this number here. So in this case, it would be 1 over 2, and it's inside the function. So I would write here half of x first. It says here translates right by 1, right? If it translates right by 1, it's inside the function. Horizontal shift is inside the function, so I'll erase this. If it says right by 1, right, I'm thinking positive, but then I have to flip it for horizontal. So right becomes left, so it's positive becomes negative, so this is negative 1. And again, I need brackets now for this function because everything is being shifted by right. And then it translates up by 3. It's outside the function. Vertical shift exists outside my function, and it's simply plus 3, right? So I have here, this here is my final answer, right? Again, I have horizontal expansion of horizontal is this here by a factor of 2. Remember, I have to put 1 over that for a horizontal one. Because it's horizontally being expanded or stretched. In this case, it's moving right by a factor of 1, or sorry, right by 1 unit, you can say, and then it's moving up 3 units, right? So again, 3 transformations in this case here. And then let's do number 8. Number 8 here says it's a square root function, right? I have square root x. So f of x equals square root of x, and what do I want? I have 4 transformations. This is a bit harder. So let's go from up to down. It says here, compress vertically by a factor of 3. If I'm saying compress vertically, again, I think a vertical stretch was a number that's greater than 1. If it's a vertical compression, it has to be a factor, right? It has to be a fraction of that. So I'm going to say here that it exists outside the function, right? Vertical stuff exists outside the function. So I'm going to say here, this is 1/3 root x as my first transformation, right? It says here reflect across x-axis. If I'm reflecting across axis, if you look back to my notes, reflection along the x-axis, the negative is going to be a negative somewhere, right? The negative here is going to exist outside my function. Reflecting up and down, you can say it's a vertical reflection. So it's going to exist outside my function here. So this negative. And then it just says here translates right by 2 units. So horizontal, right, think positive, but if I flip it for horizontal, so it's negative. So this here, I have to extend this square root because it's my entire function being shifted to the left. So I'm going to say here, sorry, shifted to the right. So it's going to be -2. And And lastly, I've translate down by 3. It's going to exist outside the function. I will have minus 3 here. So my final answer is negative 1/3 square root x minus 2 minus 3. I can check my answer again, break this down. I have a negative that says here it's reflecting along the x-axis. This 1/3 here is vertical compression by a factor of 3. This x minus 2 is I'm moving right by 3 units and then down by 3 units as well. So I'm good for number 8. And now what am I doing here? Write g of x dash line in terms of f of x, which is a solid line. So what I'm doing is I'm taking this function and I'm rewriting it as an f of x, right? So how I usually do this problem, and I'm for the sake of time, I'm only gonna do maybe I'm only gonna do 1 in this case, because I kind of want to get into this one here. So maybe I'll just do 1, and then I'll do a little review of what we did today, and then we'll move on to the next topic. So this is write a g of x dash line in terms of solid line, right? So again, I have here. How I can visualize this is I can visualize this problem just like number 1, right? If I have a parent function in blue, I want how many transformations do I have to make it to here is the same thing as how many transformations do I have to go from here to here. I have to just flip it, right? So what I can do is I can modify this problem to say that I'm actually doing the first part of the problem. I'm taking this parent function. How am I going to write it in terms of this function here? So let me just show you number 9 here. My parent function in this case is this blue line. So I'm going to do it in blue actually because it's in blue. And this here it looks like an awful lot like a square root function, right? So this is f of x equals this is square root x, right? And then what do I need to do to write the transformed function in this case? Is this a negative? This is root x, so it's fine. What do I need to do? I see my little point here. It moves left by 2. So it says here my first transformation is left by. Actually, no. Let me do this in black. So here's left by 2, and then what am I doing here? I see here that my points are, it looks like a vertical stretch, right? Because I'm not really moving more horizontally, but I can see that I'm stretching this kind of this way as well. It looks like it's increasing much faster than this one here. And then let me take 2 points to verify that. So this is 1 here, and my 1 in this case is 1. It was 1. This is 1 on here, and if I move 1, looks like it's kind of at negative 2, so that's not a very good point to take. But this point here, as you can see, negative. This point here is negative 5, and 1 negative 5 in this case, 1 negative 5, and then whereas for this function here. 1 negative 5, so this would have been moved 1 2 3, so 1 2 3. Negative 5 would have been only at about like 1, very very close to 2, so 1 less than 2. So I'm going to approximate that this is a vertical compression by kind of 3. And again, this is it's very hard for me to say it's a vertical compression, but again, I'm just taking basically arbitrary like 2 points and comparing what's being happened. And again, it's kind of very hard when we sketch this out, and I can't extend this graph, but I'm going to say here this is a vertical compression. We only know what's given to us, right? By a factor of 3. Let me just check my answer for this one, because I assumed it's 3, but let me just see, because I do have the answers here. Oh, so they did it algebraically. Oh, so this is good. Left by 2 is this here, which is awesome, because it's moving left by 2. And then I got it right. This is a vertical compression by 3, right? So that's awesome. And then, so that's good. I guessed right, because I'm only given as much info as my graph here. And then I did a little peek, but it says here again, it's going from here to here, right? So I can say this is a reflection along the x-axis as well. Sorry, I don't want to download that. This is a reflection along x-axis. So if I want to write this algebraically, it would be f of x equals reflection along x-axis would give me a negative here. Vertical compression would give me a 3 here outside the bracket here. So this would be, sorry, this is a vertical stretch, not compression. Someone corrected me. This is a stretch. I got confused. 3, and then this is root x, and this left by 2. I flip it. Left means in my head is negative, but flip it to positive. So this is x plus 2. So that's going to be number 9 for this one. This is my function from here to here. We don't know what f is, but I know from this case it's a square root function here. So let me do one last one here, and you can do these ones on your own. But I want to just finish off another question for this video, and we're gonna move on to the next lesson. Would be piecewise functions out. So that'll be fun. So look forward to that. But this here, it says identify the parent function of f of x by the equation, right? For the function given. Okay, so let's see here. I have this 13 here. Awfully looks like a awfully looks like a this would be a, if it's going this way and this way, it awfully looks like an absolute value function, right? So absolute value function. I'm gonna just write fn here for function. So I can say here this f of x equals this, right, root x. But what can I see here? I see here that it's being kind of shifted towards it used to be 0, 0 right here. So it's going to shift, this is left by 2. You can say it's left by 2 in this case, or sorry, right by 2. So my first transformation here is right by 2. And then as you can see here, it's kind of weird, right? Does this, it doesn't really stretch at the same time, or sorry, it's not being compressed at the same time as this point here at 2. Actually, no, at 2 it's at 2 here is 8, but then in this case it would be a kind of 3.5 here. So it's kind of, you can see it's kind of uneven, right? So let me just, actually no, this 6 here is also 2, right? Actually no, it's not uneven. It's not an uneven thing. So I can say, I'm gonna say that this is a because I already moved right by 2, so I'll use decimals to help me out here, but and you can use that too. What's the absolute value? Absolute x, is that what it is? No, I can't use decimals here. I don't know what the absolute function is, but let me just do this manually. So this is the absolute value function of x. I'm moving right by 2, and then I see I can kind of see it's being like squeezed, right? It's being compressed, right? So I can say this would be I would say this is a vertical compression because I'm being compressed by a factor of, I don't know what the factor is here in this case, but let me just pick 2 points and we can maybe infer. So this is a vertical compression by factor of, and with these problems it's usually 1, 2, or sorry, it's usually 2, right? But let me just look at the point here. Let me just take, so my point here was 1, 1 for a root x here, and this here is, that does not help. Let me take this point here. This is for my transformed function. This is the point. I'm going to do transform function as g of x. Sorry, t. So my transform function, this here is 5, 1, right? 5, 1, or sorry, is this 5, 1? Yeah, 5 and 1, and then my parent function was before was at this point it would have been only 1. What? Actually, no. I have to adjust for the x value first. So if this is 5 and 1 here, I'm doing a vertical compression, but I'm not changing my x value, right? So this is off by, this is 5. It's off by 3. So I've got 1, 2, and 3 here. So this would have been, would have been. Let me check. Actually, I don't think I'm going to use the 0.51. I'm going to use a point. It's kind of hard to see here. Like it's let's see, negative 4 and 2 might help. Negative 4 and 2, and I would have negative 4 and 2 would be, let's see. This is a bit hard to see, actually. I know it's a vertical compression, but I just can't find the factor in this case. This graph doesn't really tell me a lot. I want to say it's a factor of 3, because I see a point here that's 5 and 1. 5 and 1 when it should have been at 3 and 3 is my guess here, because I have here I have my parent function in this case would have been at 3 3, right? So if I looked at, it's 1 1 2 2, and I can't edit on this, I'm kind of sorry for that. So it kind of goes like, it goes like this V here, right? So 1 2 and 3. And then if I moved here 1 2 and 3, it's only at 1 when it should have been at 3. So I think I'm gonna say it's a vertical compression by a factor of 3. Let me check my answers to see if I'm correct here. Yeah, so it's 1 over 3, right? So I'm correct. This is it states that vertical compression by a factor of 3. Remember, stretch would have been 3x, but this is a vertical compression, right? So I can say that this is g of x would equal, I would have to say again, absolute value bar of 1/3 x, and moving right by 2, which means this would be negative 2. And then I would have to, it's to the entire function, right? So that's good for that one. So again, what we did today was we talked about horizontal and vertical compressions, and what we're going to do is, and we actually did a lot of work in terms of we put all our transformations together. So we did horizontal shift, vertical shift, we did horizontal reflection, vertical reflection, and we did horizontal stretch and vertical stretch and compressions as well. So that's all the transformations we need to know. For next lesson, we're going to do some work with some piecewise functions. So again, functions that are kind of discontinuous. And then, but we've already looked at that. We're just actually at this point, we're just sketching. And then we'll look at function operations and inverses as well for next lessons. So as always, thank you for watching and have a great day.